Hello everyone, nice to meet you. Today I'll be going through my project, the whole project, and also we'll be talking about the basics of PyTorch. Let me just, okay. Now, as I have talked about in my past live sessions, I'll be talking about the basics of PyTorch with an example of the project I have done. PyTorch is quite an extensive module, Python module for machine learning. It covers almost every possible aspects of machine learning, including computer vision, তারপরে voice recognition, object detection, and every other type of machine learning problems that you might face in the future. Now first of all, let's look at the PyTorch. Excuse me. Let's look at the PyTorch website. Here you can see that we have a lot of documentation, lot of documentations where you have torch audio, torch text, torch vision. All of these modules are specialized for their own purposes. For example, torch vision can be used for the image related problems. For example, object detection from an image is a vision related problem. So if you face this kind of problem, you can use this module. There is also the torch audio. This consists of voice recognition and other type of problems. You will be needing this module if you are facing or working with that type of problems. Torch takes the text as inputs and provides their expected results. So if you are using hand recognition or for example keyboard style recognition where every key is detected, that type of problem, or there is also other type of text related problems, machine learning problems, you can use this module to solve. There is also the basics PyTorch module, which you will be needing if you are working with PyTorch. Now let's see what other things you will be needing. If you look at this side, you can see all of these modules and functionalities and other things that are included in the PyTorch module. Let's start with the neural network. Let's start with this neural network. The neural network is quite a conventional machine learning tool. You have heard about neural network probably if you are doing this class. For example, convolutional neural network is a type of neural network. There is also the recurrent neural network, RNN, and also other type of neural networks like TNN, ANN, and such. Neural networks are, let's see a image on neural network. These type of things, neural networks are made in such a way that it acts like an human neurons. The neurons which are found in human brains. So this type of neural networks works in a way that our brain processes outside signals. So for example, if you provide 4 types of inputs in this network, after going through multiple layers, for example, this one is a hidden layer, this one is a hidden layer. After going through these layers, you can get a 2 output here. So given 4 inputs, you are getting 2 outputs, and the hidden layers are helping you in getting to the right output. So this is the basic neural networks that you will be working with. in current machine learning problems you will be facing more complex type of neural networks which doesn't just take a fixed input and fixed output. There might be lot of different type of neural networks connecting together. For example, you can have a convolutional neural network connected to a recurrent neural network, or you can have a dense network where every node, one of these circles is called a node, so every single node will be connected to a different node. Or for example, here the input is connected through the hidden layers to the output layer, but in dense node you can probably have that this node is connected directly to the third layer, or for example in the output also. This type of different networks are quite helpful. Let me show you a few examples. Dense net. Here you can see dense net is a type of convolutional neural network. These circles are the what do you say? These squares are filters. Filters, for example, if you have an image and it's an RGB image, then you have 3 channels. These 3 channels can also be called 3 filters in terms of convolutional neural network. So for example, if you give a 3-channel RGB image, you can extract more information from that 3 channel into more channels or filters. Here you can see from 2 squares you are getting more and more smaller but more channels. And as I was saying, in dense net you can also see that every layer is connected to every other layer, and it's quite densely connected. That's why it's called a dense layer. Now there is also an interesting ResNet. ResNet is kind of the uses the recurrent principle. ResNet uses the recurrent principle, and it connects in every other layers. As you can see, it doesn't connect densely as the dense layer, but it connects to every other layers. This helps. How does it help? For example, it can help in a way that if you are giving an image as an input and you are going through a lot of hidden layers, then at some point you might lose the initial data or initial shape of the object. So it's good that you are reconnecting the initial. For example, let me show you something. Let's just show it here. As you can see, you are going through the weighted layers, but after a few layers it might be quite difficult to recognize the initial input that you have given. So it's useful if you add the initial value and then continue with your path. For if I give an example, what would it be? Let's say you are giving an exam. So if you look at the question paper and you are writing the answer, you will be going back and looking at the question paper multiple times during your 2 hours exam. You are not required to remember the question paper whole and then write 2 hours of exam. You will need the help of the question paper multiple times during the full 2 hours exam. So you can think of it like that. Your network will not have to remember the input in every single weighted layer. It can go back to the initial paper, for example initial input, and then giving the giving the output of a simple weighted layer, it can just judges from here. As you can see, after every 2 or 3 hidden layers, you can just go back and look at the initial input and then just go it from there. These are some of the examples. As you can see, ResNet 152. This 152 number is the number of the hidden layers or the chunks of layers. For example, this one is a basic chunk or a simple layer. This is a simple layer, and in ResNet 152 you have about 152 of these similar layers. So that's why it's a very big network if you consider it. There are multiple variations of ResNet. For example, the most basic is ResNet 18, which is the smallest version of ResNet, and from 18 you have ResNet 34, ResNet 50, ResNet 101 and ResNet 152. These are the samples of ResNet. There is also an Inception ResNet version 2. This is also a variation or a network that is takes some type of some inspiration, you can say, from ResNet and extended in that on that, so to make it a lot more complex and a lot more useful in their own respect. Let me see. Now what more? Okay. Now as I have talked about the neural network, now what are the few components that you might be needing in building a neural network? Let us see. As I was saying, there is convolutional layers, there is pooling layers, there are spreading layers, nonlinear and all other recurrent layers. As I was saying, there are various types of layers and other things. As you can see, if you look at this documentation, you will find a lot of interesting things, and these layers are just the basic building blocks of your network. In your network you might have a small network or big network, but this will be the building blocks using which you will be creating your full network. There is also functionals, as you can see, conv 1D, conv 2D. These are convolutional network. As you have seen, they are the I have shown the squares. As you can see, where was it? These squares. These are the 2D convolutional layers because there is only 2 dimension. As you can see, you can have multiple dimension. You can have 1-dimensional convolutional layer, 2-dimensional and 3-dimensional too. So you don't have to be afraid of any creating any new innovative things. You can create those using these basic building blocks, but you don't have to create the blocks to build your network. These are very useful in PyTorch, and it has given PyTorch has given you a lot of useful tools. You can just use these tools to create your own networks. Excuse me. Excuse me, just let me check something real quick. Sorry about the delay. I didn't notice that my webcam was frozen, so sorry about that. Now let's continue. Okay, let's drop that. Now these are the basics of our neural networks, and also what are the basics building blocks of machine learning. As you can see, these are just the tools you will be needing. These are not the what you can see. You will only be able to apply this if you know the basics behind what you are building. So until you learn what type of network you are building, you may not even need this. Now let's see one of the basics, the tensors. Tensors is quite important in PyTorch. The machine learning, the machine learning, the learning that happens in PyTorch, you can't what do I say? Most of the calculations. What is machine learning? It's the calculation the computer does to predict something. So the calculation is quite important, and the tensors are the form of data that the calculation is done on. For example, as you know, if you are from computer the background programming background or such, you will know that there is a different type of data types. For example, float, integer, and other type of data types. Tensor is a type of data, type which is mainly used in this type of things, and it's quite compatible with the GPU and also CPU, depending on which device you are running your network on. You will be needing different type of tensors. As you can see, these are the basics data types which are related to Torch, but as you can see, if you are running your network on CPU or GPU, your data type will be changed to a tensor. As you can see, there are a lot of different types of tensors depending on which type of data you are using. You can't work on a specific you can't work on a data type directly. What was I saying? Excuse me. For example, if you are working on an image, the image will be converted firstly to integer or float. You will be reading that image from your hard drive or from the internet, and that the data type will be that. But if you are going to be using that image as in your network, then you will need to convert that image into a tensor. It will create a specific tensor of that image. Tensor is nothing but a specific way to represent a data. Let me show you an example. import torch x is equal to 10x. As you can see, I have just put 10, which is an integer, into x, and if we get type of x, as you can see, the type of x is an integer. Now let's see, y is equal to torch dot tensor of x. Now y has x as a tensor, so if I print y, it's the tensor of 10. So I just converted my integer 10 to a tensor 10. So if I try to get the type of y, it's a torch tensor type, and in torch tensor's type, I didn't provide a specific data type when I assigned x to the x to be a tensor. So here I can provide a specific data type is equal to let's let it be a torch torch type. As you can see, my torch just became an torch integer of type int32. I can also make it float, I think. Now it just became a tensor of 10.0. Most of the time you will be using the float type because our network mostly works with float type, so it will be that. Now tensors can be quite interesting. Here I just gave a single integer into a tensor, but you can also make it quite complex. For example, if I let's just keep it that way. Let's transform here. Let's make it a list. Now x is a list, it's the type of list. Now I can just assign x into a tensor. Now y became a tensor. As you can see, its data type has changed from integer. In this list, all of this data is integer type, but in my y variable, as you can see, the tensor consists of a list which consists only floating data, specifically float 32. As you can see, the type of y is also constantly being tensor. It doesn't change at all. Now what is the fun thing about tensor is you can make the tensor as big as possible or as small as you need. How big a tensor you will be needing? Let me give a simple example. In our modern day, the one image, for example, if you have a 2K image, then its size will be probably about what will be size 5 megabyte or 10 megabyte, I'm not sure, but it will be about that size. But what if you have 1002K image? What will it look like? It will be about 1000 list of a 3-channel input. Now let me show you. I have for example, I have 1000 image, 1000. This is not right. For example, I have 1000 image every image is an RGB image. So RGB, there is 3 channels. So every image has 3 channels, and 2K image. So let's see what is the 2K image. 2K in pixels. So every image has a pixel of 2560 1440. So 2560 into 1440. So this is basically, as you can see, this is the size of our tensor. Now if you are not quite sure about how big this is, then let me just show you. Let's print. Let's do a copy. How big is this tensor? No. Now this tensor is 1 2 3 4 5 6 million billion, around 11 billion byte, I think, every kilobyte or byte, pixels, 11 billion pixels. This is the size of 1000 2K image. In real world, you might be required to work on hundreds of thousands of images, which can vary depending on what type of image you are working with. If you are working with a small size image, like 500 by 500 pixel image, then you might not need so much data. But if you are working with high resolution image, then it will be quite expensive on your GPU or in your CPU. A RGB image, in an RGB image, every single pixel consists of a lot of data, so it will be quite computationally expensive if you try to handle a lot of data in a single tensor if your GPU is not big enough. In my 8GB GPU, if I am working with my machine learning model, let me give you a comparison. When I am playing the Assassin's Creed, the latest Assassin's Creed game, my 8GB GPU only takes about 5.5 gigabyte of memory. But when I am working with my machine learning model, the GPU is 7.5 gigabyte full. So as you can see, it's more expensive than my game. So it's quite computationally expensive if you try to put a lot of data, but you may require to do so if you are working with a lot of data. So let's see some more examples of how tensors can work. This is a one-dimensional tensor. You can have two-dimensional tensors like this. This is a two-dimensional tensors. Now you can have three-dimensional tensors. This is a three-dimensional tensor, so you can have as many dimensions as you need. Let's see what is the shape of this. You can also check, you can easily check the size of each tensor just by using the shape keyword. So you don't need to keep track of all how large or how expensive or how big your tensor is. you don't need to do that. If you are given a big tensor, you just need to use the shape keyword and you will be given a simple size of your tensor. As you can see, this is 2 by 3, 2 into 3 into 3 by shape of tensor. If you want to visualize this tensor, then I have a good idea. Just torch.rand. This will provide a random integer of random shape, not random shape. I am giving this shape, so it will, as you can see, my memory is full. There is no more RAM to allocate. So let's see my task viewer. The temporary memory has been full, so as you can see how memory intensive this can be. So let's just drop it to 200 by 200. Now I can see my Z. As you can see, this is my tensor. Now if I try the shape, as you can see, the shape is 1000 into 3 into 200 by 200. This means I have 1000 image of RGB channel, which is a 200 by 200 image each. Now this is the basics of tensor. And you will be working with tensor a lot, so it is a good idea to get a good understanding of tensors, so you won't be constantly sorry, it's quite cold here. You won't have to constantly be reminded of what you need to do. As I said, tensor is quite important if you are using PyTorch and if you are working with machine learning. And most of the raw data that you will be getting, for example, image, text, or what do you say, audio or video and other type of data, you first have to convert that data into tensor, and then you have to compute in your model. Here comes one of the basics. Let me just go to a new now comes a tricky. Can I have flowchart? Can I have a basic flowchart here? Flow. Now here comes the matter of pipelining. I don't need the business model is a machine learning pipeline. Here comes the pipelining of machine learning. What is pipelining? Pipelining is basically the streamlined process of a machine learning problem solving, something such. Now when you first start to do machine learning, what you are basically doing is solving a problem. Just like a programmer which solves a basic problem, you are doing the same thing but in a complex way. Let's first see what are the processes. So in a machine learning pipeline, the first thing that you will need to do, the most basic thing that you will need to do is collect no, that will be later part. The first thing that you will need to do is identify the problem. The most basic, the first question that you need to ask yourself is what is the problem you are trying to solve. For example, you might be solving the problem of object detection, where you will be detecting a object in a image, for example face detection or vehicle detection, such problems. Or you might also be working with audio, then you will be doing voice recognition and other problems. So the first thing in machine learning process is identifying the problem. What is the type of problem you are trying to solve? You can process the same problem in different type of ways also. For example, in a computer vision, you can try to detect object. You can detect a particular object in a image, in an image, or you can do image segmentation, which is pixelating the object that you are trying to detect. You might also be doing identifying the object, what type of object you are detecting is. So you can have the same problem, but you can approach that problem in different way. So it's very important to identify what type of problem you are trying to solve. The second stage would be collecting data. Now, after identifying what type of problem you are trying to solve, you will need to collect all the related data to solve that problem. For example, if you are trying to do object detection, it's quite important you have a lot of images, so your model can identify a particular object from a variety of images. So it's important to collect a lot of data related to your problem. The third stage would be what is process pre-process. The third stage would be pre-processing. Pre-processing, what you are pre-processing? We're pre-processing the data that we have collected. A collected data can be in many forms. For example, you can have a survey. If you are working with a survey or a particular problem, then you might need to process that all of that survey data into a specific type of a specific form, which will be quite helpful in your machine learning model, because your machine learning because your model will be taking certain inputs and giving you certain outputs. So it is important to identify what your input will be and what you are expecting your output to be. So it's quite important to know these things and to process the data that you have collected in a form that won't be complicated for your model to handle. It will be easier for your model to handle, and it will be also be easier for you as a user or as a developer to process, I think. So pre-processing your data, pre-processing your data is quite important in this process. So let me show you an example why pre-processing is needed. here you can see this is my data set. So what I am doing is reading data. For example, let me show you. If can I show this? Okay. For example, image wallpaper. For example, if this is supposed to be my input, then I am expecting to process this input in my model. What I am doing is, firstly I am reading the image that is saved in my hard drive or other places. For example, you can read this image from a cloud or other place. In a digital space, you can read this input as an image. The next step you can do in pre-processing is you can resize that image to fit a specific dimension. As in here I have resized the image, I have resized the inputted image into a specific dimension because I need my model to work on a specific dimension, image dimension. So I have resized my image. This is a pre-process I have done. The next thing I have done is converted the image into a tensor. As I have said, machine learning model in PyTorch mostly work with tensors, so it's quite important that I have to convert the basic raw data of the image into a tensor. So I have converted that data into a tensor. The next thing I did was convert, since I have read this image, CV2 is a Python module that can do a lot of computer vision problems. So in here I am read function has what it has done is read the data from my PC, but it has read it in a BGR format. So I have to convert that BGR to RGB format, and I have done that in this line. And I have also divided it by 255 because as you know, RGB format and each pixels can have 256 variations. So I have divided it by 256, so my basic range of my data is from 0 to 1 and it doesn't exceed that. So, and the next thing I have done is convert that RGB data to lab data, RGB format to lab format. RGB is red, green, blue format, and lab is another format of image. Here L is lightness and A and B is something, let's not talk about it. So L format, why I have converted it to lab format. Lab format is quite useful here because I am working with a colorization problem where you have to color a grayscale image. Here in lab format, the lightness or L channel is already the grayscale format, so I don't have to convert my input to any lab format. I can just take the L format, I can just take the L as input and set my target to A or B. The next pre-processing I have done is some conversion of channels. For example, if my data is 3 into 200 into 200, then I can just change the way the tensor fits. So it's not quite important here. So that's the importance of pre-processing. you need to pre-process your data, so you don't have to be be overwhelmed every time you want to work with your module. So what will be the next step? Excuse me. Now, after pre-processing your data, identifying your problems, collecting the data, pre-processing, the next step. Let's see the next step. Show pre-processing. The data set can be pre-processing. Let's just say the next step. This is not a conventional pipeline. This is my pipeline, the machine learning pipeline that I use. Sorry, there is some typo here. This is the machine learning pipeline that I have used in my module, my machine learning module. So as you can see, if I go by that, the first thing that I did was identified my problem. My problem was colorization, which is the problem of colorizing. Let's just go here. Colorization is the process of colorizing or giving color to a black and white or grayscale image. So this is the problem. Now I have identified the problem, but there is some specifics that I need to do. First of all, in a machine learning model, what you are doing is giving, let's see. Now let this be your machine learning model. What you are doing is this is your now if this is text. Now I have my input and I have a machine learning model and I have my output. In identifying the problem, in this step, what I need to do is think about what my input will be and what my output will be, and the machine learning model, the creating of the model comes later. The first thing I need to do is identify what my input will be and what I am expecting my output to be. So my input in my colorization problem, my input is the grayscale, this part. My input is the grayscale image, and my output, what I am expecting my output to be is a colored image or RGB image, or it can be a layer image. Basically it needs to form a full colored image. So in my problem, what I am giving it, as you can see in my data set, what I am giving the input image, input and target image. I am giving the L channel, which is also the grayscale channel. I am giving the L channel as my input, which is a single one channel. Excuse me, which is a single channel as my input, and I am expecting the AB channel to be my output, which is 2 channels. In total there is 3 channels, but one of these channels is my input and 2 of the other channels is my target. And the target, what is a target? A target is basically a data you are comparing your output of your model with. For example, if I give the if I give the grayscale or L channel to be my input, at the beginning my machine learning model will not work as well, so my output will not be as expected. So what I need to do is compare that output to something, and that something is the target. So if this is my target, so after giving the input to my machine learning model, I am getting an output, and this target is my expected output. What my expected output is in training phase, in the training phase of my model, I know the expected output. This is the supervised, I am talking about the supervised learning, so I know what my expected output will be. For example, in my training phase, I won't be working with these old images which I don't have the colored image of. I will mostly be working with modern images which I will convert to grayscale. So I have the grayscale input and I also have the colored target image. So I don't have problem when I'm comparing the expected output. So as I said, target is equal to expected output. This is my input, my machine learning model, and this is the output. My target is the expected output. Now in machine learning, the two most important things is fitting or optimizing your model, and you will be doing that by calculating the loss. And what is the loss? What is this loss? Now there is a lot of different kinds of loss functions. Now the basic concept of loss is the difference between my expected, or you can say my target, and output. A loss is the difference between my target and the output. So if I am giving 1 as input and my target is 3, but my output is giving me 5, then my loss will be 3 minus 5 will be -2, but since it's the range, then it will be just 2, so my loss is 2, and I will be based on this loss, I will be trying to optimize my model, and as we do it continuously, giving input, getting an output comparing it to my target, finding my loss, and optimizing my model. As we go through this process continuously, my model will be optimizing little by little, and that's the process of how the machine learning process works. This is the supervising machine learning, so keep that in mind. This whole process is the process of what my model looks like. So at first I am giving the grayscale image, which is grayscale image, and also the L channel. This is a single channel. As you can see, this only has a single channel input. So if you convert it to a tensor, then it will be the shape of this tensor will be 1 into 256 by 256. This will be the shape of this image. So I am giving this as my input, and I am choosing between these two. I'm choosing between these two models. My model is, I have designed my model to work with different types of pre-built models. So here you have the UNet++ architecture, and here is the normal UNet architecture. So you can use any of these two architectures in my model. You can also change the encoders based on your configurations. For example, there is a lot of encoders, ResNet 18 to 152. You have also the Inception ResNet and Efficient Net. These are also all the encoder choices that I have given. So my input is fixed. This is a grayscale image. My architecture can be changed based on your choices. There is two choices, UNet and UNet++. The encoder part, also the architecture I am using, UNet and UNet++, is an auto encoder, meaning it has an encoder and decoder part. These two part combined gives us an output. So I am not changing the decoder. The decoder will be built based on my encoder, but I am choosing my encoder here. You can see these are the given encoders. You can choose any of the encoders, and you can build a custom model based on these two inputs. From here you can, after going through this, you can get these two. As you see, this is the L channel, which is basically the grayscale image. This is the L channel, and what I am getting as output is this A and B channel. And combining these three channels, combining L, A, B, these three channels, I am getting the lab format. I am getting the lab format image. And if you combine these three channels, as you can see, these three channels are not similar. It may look similar, but as you can see, there is a difference in lightness and other things. So combining these three channels, I can get a lab format image, which is a colorful image. And this part is my loss calculation, which consists of which type of embedding you are using, which color space you are using your embedding on, which loss function you are using. Depending on that, I will be calculating my loss. Let's come to this later. Now let's go through this from the start. Let's go to now. This is the data set I have built using my images. There is a lot of images, and in every get item I am only getting a single piece of data, which is my image input and target. The output I'll be getting in later, and I'll be comparing that output to my target image to get the final result. This is basically my network. My network is not very big because it uses a lot of other modules, Python modules that have been pre-built. What I have added here is the use of those pre-built modules to create a new type of output, and using a combination of those architectures and those encoders and a loss function that also already have been created but haven't been used in this type of problem solving. So I have combined all of this process to create my own variations of a solution. So even if my network is looking short here, it's not this in actuality is not this short. It's a very big network. As you have seen here, it's a quite complex network, but I have used the most essential parts of that network, and I have used that to create this model. The main ingredient of this process is probably the color function, the loss function. The loss function uses different type of embedding and also different type of losses and different type of color space and other things, and it produces a specific loss functions that you are giving the parameters for. So based on that, I have got a loss function. What my next step would be to is train the data. I don't think let me just give a quick tour of what my data is what I am doing here. I don't think I will be able to completely explain everything. I'll be showing the results of my process, so just follow me. Here in the train method, what I have done is this model. I have given my input into this model to get the predictions, which is the output that I have shown here. This output can also be shown as predictions. So this is the prediction, and this is the target and input. What I have done here in the loss function, I have given the predictions and targets to compare these two tensors and give me a specific loss on that target. The next step is the evaluation. This is quite similar to the train function, but in the evaluation evaluate evaluate evolution sorry in this method you are you are looking at the how your model is performing, but you are not optimizing the model. As you can see, in the train function you are optimizing the model, but in the evaluation method you are just looking at the output, you are not optimizing the model. In the fit method, yeah, you are just doing the fitting, nothing major. As you can see, there is a now now let's see some results. Now these are the most working models that I have. Let's see some results here. These are the more old images that doesn't have any color variations to compare it to. So as you can see, it provides a quite colorful output given very basic inputs. As you can see, the grass color, the grass is quite colorful, the river, even if the color is not quite correct. As you can see, there is a lot of potential here. Now see some others.